So for a zero order reaction, the first thing I want you to know is the rate law. And the rate law of a zero order reaction is given by rate is equal to K, the concentration of the reactant, raised to the power 0, which is simply equal to K. Second thing that I want you to know about a zero order reaction is the half-life. So the half-life is given by half-life is equal to the initial concentration. Please take note, this is initial concentration divided by 2 times K. The other thing that I want you to know is what else should you know? Okay, the integrated rate law itself. Integrated rate law. So for a zero order reaction, the integrated rate law is given by the final concentration is going to be equal to negative Kt plus the initial concentration. So because of what you can see here, if we were to plot a graph of this reaction of a zero order, if we were to plot a graph, what you would see for that graph is that the graph will be something like this. What are these things really representing? So from what we have, this same integrated rate law, it is in the form y is equal to mx plus c. So this is telling you that the y-axis will simply be the concentration. So here we have got the concentration of A. The x-axis is going to be time. And then the gradient of this line, the gradient is given by negative K. So if they told you that you have got a zero order reaction, and once you plot a graph, the gradient of that line, let's say they tell you is 7. What is the rate constant K? So just know that gradient is equal to negative K. So therefore K will be negative 7. So it's important for you to know that. And you can see the way the slope goes, it slants downwards. Now how about if we are talking about a first order reaction? So for a first order reaction, what you should know, starting with the rate law, the rate law of the first order reaction, rate is equal to K. You get a concentration of the reactant that should be raised to the power 1. The other thing that you have to know is the equation for the half-life, and that is going to be half-life is equal to natural log of 2 divided by K. Is different from the other one, the zero order, where it was the concentration, the initial concentration divided by 2K. This tells you that for a first order reaction, the half-life does not depend on the initial concentration of the reactants. It just depends on the rate constant alone, that's all. And then when you look at the integrated rate law, so it's important for you to again understand the integrated rate law. So the integrated rate law is going to be, so this one, it's only first order that has got a natural log in it. So it's similar to a zero order, but the difference is that you have got natural log of the final concentration being equal to negative Kt, and then plus natural log of the initial concentration. You see it's very similar. The only difference is the introduction of a natural log. So if you were to plot a graph for a zero order reaction, the graph would also look similar. But the only difference when you look at this graph from that of the zero order reaction is that our x-axis is still, so this is in the form y. In the form y is equal to mx plus c. So our x-axis is still having time, but the y-axis has changed. The y-axis is the natural log of the concentration of the reactant, and then the gradient of this line is now at, it is still at negative k, so it hasn't changed. Okay, and then you also have the y-intercept. In this case it's natural log of the initial concentration. So that is it about this one. And then the other one that you have to understand is the second order. I think just these three: second order reaction. So for a second order reaction, starting with the rate law, the rate law is going to be rate is equal to K multiplied by the concentration raised to the power 2. And then the half-life is given by T half is equal to, here it is 1 over K multiplied by the initial concentration. It's only zero order reaction whose half-life does not depend on the initial concentration of A. And then the integrated rate law in this case is going to be, it is the only one that contains some fraction, so 1 over the final concentration. It is similar to zero order, except you have got fractions, and then the gradient here is positive. You can see there's no negative kt, it's positive kt. Then plus 1 over the initial concentration. So that is how you get to find these guys. And when you look at the equations, if you were to graph a second order reaction, how would it look like? So it would be, the graph would be something like that. So it has got a positive gradient, different from the others where the gradient was negative. So this is also in the form y is equal to mx plus c. So in this case the y-axis is going to be 1 over the concentration of the reactant. X-axis is still the time, but the gradient isn't going to be equal to negative x. Instead it's going to be equal to positive x. So gradient is equal to not positive x but positive k. And then the y-intercept here is going to be at 1 over the concentration, the initial concentration of A. So that is that. Okay, let me give us some questions we see. Let's say they tell you that they give you units and then they ask you to determine the unit of the third order reaction. So number 1, what are the units of a third order? Actually, the units for what? What are the units of K? The rate constant for a third order reaction. Now when you want to find the units of K, unit of K is equal to the molarity raised to the power 1 minus n, and then the time raised to the power -1. Since this is the third order, it's going to be molarity raised to the power 1 minus 3, and then time to the power -1. Depending on the time, it can be in seconds, minutes, hours, days, years. So this is going to be molarity raised to the power -2, and then time raised to the power -1. This is the unit. If it's MCQ and then you don't see this unit, molarity is also mole per liter or decimeter cubed. So I'll put mole per liter, and this is raised to the power -2, and then time to the power -1. If I take the liter on top, it becomes mole. I can put liter here. The liter now will be raised to the power -1 because it has gone up. Raised to the power -2, and then time will be raised to the power -1. If you distribute the -2, liter -1 times -2, that will just be liter +2, and then you are going to have more -2, and then you have got time -1. So this is the unit of the rate constant K for a third order reaction. Does that make sense, guys? So the next, number 2. Let's say they give you a question to say the initial concentration of a reactant, okay, in a zero order reaction. Let's say they've told you this is a zero order reaction. I'm just trying to summarize it. I don't want to write the entire question. And then the initial concentration, let's say it is at 0.75 molar. And then they also tell you that the rate constant K is equal to 0.015 molar per minute. Now, just looking at the unit, even if they didn't tell me that this is a zero order reaction, I should tell that this is a zero order reaction just by looking at the unit. How do you tell? So remember, unit is given by molarity 1 minus n, and then time to the power -1. It should be equal to this unit, which is molarity to the power. This is +1, isn't it? And then time, if I say per, it is the same as me saying minute to the power -1. So this is the same as this, meaning that the power of molarity should also be the same. So 1 minus n should be equal to +1. I'm going to take 1 this side, I'll take n this side, so it becomes 1 minus 1 is equal to n. So n is equal to 0. You can see we can tell this is a zero order reaction. So please don't struggle if they don't tell you the order of a reaction. If they've given you the unit of K, you can determine the order. Okay, so you have got the zero order reaction. The initial concentration is there, the rate constant is also there, and then let's say they ask us what will be the concentration after let's say 15 minutes. So determine A, the final concentration at 15 minutes, and then let's say you also have another one, B, how long it will take for the concentration to be reduced to. So T for concentration, so for the final concentration to be reduced to 0.6 molar. That should be in molar. Okay, so how do we answer this one? Starting with the first one, we want to find the final concentration. And we know this is a zero order reaction, so we need to know the integrated rate law. The final concentration is equal to negative KT plus the initial concentration. The final concentration is what we want, so that will be equal to negative K is 0.015. The time is after 15 minutes. Initial concentration is 0.75. If you punch that on your calculator, you get 0.525 molar. And then for B, we'll still use the same equation. Final concentration is equal to negative kT plus initial concentration. But this one, want to find the time for half-life to be reduced to 0.6. Please understand English. If they said find the time for half-life to be reduced by 0.6, it is different when they say to be reduced to 0.6 by 0.6 to 0.6, two different things. So to 0.6 means that the final concentration should be 0.6. Actually, this is 0.06. So 0.06. So right there 0.06. That will be equal to negative. Remember, K is 0.015, and then times the time which we want, and then the initial concentration here 0.75. What I'm going to do is I'm going to get this guy, take it to the other side of the equation to become positive 0.015t. I'll get this guy and take it the other side, so it will be 0.75 minus 0.065, and that will be 0.69, and then divide both sides by 0.015, and that is going to give us around 46 minutes. That is how you get to maneuver around that question. Okay, hope that makes sense. Let's do probably one more question, then we are good. This will be the third one. Say they tell you to calculate the concentration of a reactant that takes 47 minutes for it to reach a final concentration of 0.15. Okay, so calculate the final concentration of a reactant that takes, let's say, 4.7 seconds for it to reach a final concentration, to reach final concentration. So okay, the question is not to calculate the final because I'm giving you the final. So calculate the initial concentration of a reactant that takes 4.7 seconds to reach final concentration, which is equal to 0.15 molar. Given that K is equal to, say, 2.5 times 10 to the power negative 3 times 10 to the power negative 3 molar to the power negative 1 second to the power negative 1. So you can see for this question, rate constant hasn't been given. So rate constant has been given, but the order of the reaction hasn't been given. So you first need to know the order of this reaction. Just look at the unit of K. Molar to the power negative 1 second to the power negative 1. This should be equal to molar to the power 1 minus n, and then time, which is in seconds, in this case to the power negative 1. So equate the powers of m. So negative 1 should be equal to 1 minus n. I'll take n this side, I'll take negative 1 the other side, so n is going to be 1 plus 1. So this is the second order reaction. And you know that for the second order reaction, the integrated rate law is 1 over final concentration is equal to positive kT plus 1 over initial concentration. So this will be 1 over the final concentration is 0.15. That will be equal to K is 2.5 times 10 to the power negative 3, and then multiplied by T, which is 4.7, and then plus 1 over the initial concentration. That's what we're trying to look for. So at this point we have got 1 over 0.15. If you multiply 2.5 times 10 to the negative 3 times 4.7, you get a 0.705. Then we have got plus 1 over the initial concentration. We'll get this guy and take it this side, so it will be 1 over 0.15 minus 0.705. That should give you 5.9617. That will be equal to 1 over initial concentration of A. For me to find the initial concentration of A, therefore, since initial concentration of A is in the denominator, I'll take it in the numerator. And what will happen is that this number is over 1. So if I take 1 down and then A on top, I'll swap also this side. 1 will go up, 5.96 will come down. So it will be 1 over 5.9617, and that will give you 0.167 molar. So this is how you get to determine the concentration. They can also ask you, let's say, find the half-life. So if this was asking us to find the, say, half-life, okay, calculate A and the half-life. The half-life for a second order reaction, the way we could have found it is half-life is given by 1 divided by K, the initial concentration of the reactant. So it should have been 1 over K is 2.5 by 10 to the power negative 3. Multiply that by the initial concentration, which you've just calculated, of 0.167. So whatsoever it will give you, that will be the half-life, and it is in seconds. So that is how you work out these things. Very easy to apply, very easy for you to be able to work out. Just something for you to think of. Let's say they told you you have got let's say a first order reaction, isn't it? Let's say they said you have a first order reaction whose concentration, okay, listen to the English. You have got a first order reaction. Let's say the rate constant K is, let's say, 1.5 molar, the power negative molar. Actually, for a first order reaction, the rate constant is just second to the power negative 1. And then they tell you that for this first order reaction, the concentration dropped by 50%. What is going to be the time for it to drop by? Okay, let me say the concentration drops by 20%. Okay, initial concentration reduces by, let's say, 20%. And then they say calculate T. So the way you find T is you first need to find the initial concentration. Let's say if the initial concentration A is X. Okay, there is a mic that is open in the background. Can't close it. So if the initial concentration is X, what will be the final concentration? The final concentration, remember, the concentration is dropping by 20x. Okay, it's dropping by 20x. So we are going to have 20% of x So this is what? This is 0.2x. This is how much we have dropped the concentration by. So the English here for you to understand is what is remaining, since this is how much we have reduced the concentration by. Okay, we've dropped it by this amount. So what is remaining? So what will be remaining is the total amount of concentration we're supposed to have is 100. So from that 100, remove what you've dropped the concentration by, because you've dropped it. Let's say if they say I've got 100 kwacha. Oh, I've reduced my 100 kwacha by 20. If you reduce it by 20, what means? What is the meaning? Where is it now? It is now at 80. You've reduced it by 20. So you've dropped the concentration by 0.2. But what do you have? It is, so the final concentration therefore is going to be 0.80x. Since this is a first order reaction, natural log of the final concentration is going to be equal to negative kT plus natural log of the initial concentration. And what I can do here is I'm going to get kT and take it this side. I'll take natural log and take it the other side. So that will be kT is equal to natural log of the final initial concentration minus natural log of the final. So this will be, where there is K, we'll put our 1.5 there, and then T, that will be equal to natural log. So you people are coming from doing mathematics in high school. When you have got logs of the same base subtracting, what you do is you divide them. So it will be natural log of the initial concentration, which is x, divided by final concentration, which is 0.8x. Okay, so therefore the time is going to be natural log of 1 over 0.8 divided by 1.5. So whatsoever that you find, that is going to be the time that it will take for you to drop the concentration by 20% for this question.